Okay, now I'm going to go over problem number 11 in the problem set. This is the one where you're looking at satellites that are in geosynchronous orbit. And the reason that they're in geosynchronous orbit is because you want the satellites to exist right over a specific spot, or to be directly located over a specific spot on Earth. That is, it takes them 24 hours, the same amount of time it takes the Earth to rotate once. So if the satellite happened to be over a spot in Ecuador, then it will remain in that over that spot in Ecuador forever. So therefore, if you're setting up any sort of type of communication systems where you're using the satellite itself, whether it be GPS or whether it be for television or something like that, you would always have that satellite directly over that spot on Earth. So if you were setting up like a dish that's pointing towards that satellite, you don't have to adjust where the dish is pointing based on the time of the day or the time of the year as that slowly moves across the sky relative to the spot on Earth. Okay, so what do we know? We know that the period is equal to 24 hours. Do we know anything else? Oh, so we'd have to look up what the mass of the Earth is. Mass of the Earth is given. I might actually look that up on Google or something like that. So that's what I will know. I know what G is, big G. That's not going to change. That's a universal constant. It's the same wherever you go. Very, very small, which gives the magnitude of the force of gravity. So our first deal is how far away does the satellite need to be placed for it to be in geosynchronous orbit. So we're trying to find what this is. This R, that distance from the center of the Earth to the satellite. If I wanted to find out what the distance is from the surface of the Earth to the satellite, then I just have to subtract off the radius of the Earth. And then I'd be finding this distance right here. So let's see here. We know that this little satellite, if I were to draw this satellite, is going to have the force of gravity on it, no matter where it is. If it's as it rotates about the Earth being the center here, it would have the force of gravity towards the center of the Earth. And that force of gravity is providing the centripetal force. So I'm just going to look at the sum of the forces is equal to MA, and this is AC. And so now, as I take this further, I break this apart. The only force on it is Fg, is now equal to M, and I'm trying to figure out how far away it is. So I'll do V squared over R. Okay, and right here I have the period. So let's work on that period a little bit and see if we can get that directly into a way that we can plug it in for the velocity itself. So I'd want to convert this into seconds. So this would just be that we know there's 3,600 seconds in an hour, and so we just multiply that by 3,600, multiply by 24, right? And you could do some dimensional analysis if you feel more comfortable with that, but I'm not going to work on getting that down to seconds. I'm going to actually assume that you guys can figure that out. So we know that velocity is equal to the change in distance over the change in time. This change in distance, so we're talking about the period of time for it to go around once. So that distance is going to be 2 pi r. That's the circumference of the path that this satellite will take at that distance r over the period. Now let's plug that in over here for my force of gravity is equal to mv squared over r. So I'll plug it in for v squared is equal to m. Now I'm squaring this, so that ends up being 4 pi squared r squared over t squared. And this is right here is r. So now let's see here. I can cancel out one of the r's here. That's about all I can do. But over here, now that it's, as I get further and further away, the force of gravity is, or the gravitational field strength is going to become weaker and weaker and weaker. Here on the surface of the Earth, it's 9.81 newtons per every kilogram, and as I get further away, it becomes less and less and less and less. So let's see, we'd want this formula then, m, and this is the mass of that satellite, what we're looking at here, and also here. The mass of the Earth, what it's orbiting about, r squared, is now equal to this m 4 pi squared r over period squared. We cancel out the mass of the satellite itself. Doesn't matter what that mass is. It could be a moon, it could be a satellite, it could be a wrench that was dropped by an astronaut at that elevation and is moving around the Earth at that orbit. So now let's see here. I'm going to pull all of my constants over onto one side. ME, that's a constant. Let's see here. Then I end up with over 4 pi squared. This is going to be equal to r cubed over t squared. So here we go. Now, what are we actually looking for? How far away it is? So I just solved for r right here. And that would be the answer to the first part of this problem. What would the gravitational field strength be at this point? Oh, so if we're looking for gravitational field strength, what we're doing is we're looking for what Fg is. So in this case, I will solve Fg is equal to g m1 m of the Earth at this distance. I'll call r squared. I could call it d squared, but just because I have been dealing with a circular path, it's easier to look at it in terms of radius. But it is the distance to center of mass to center of mass. So I know that in this case I'm trying to find this g. So I have mg is then equal to g m of that object, me over r squared. It's independent of what that object is. So remember, g is in newtons per kilogram, so it doesn't matter how many kilograms of matter that you have, it's still going to end up being multiplied by this field strength to figure out what that force of gravity is. So we end up with g is then equal to g mass of the Earth over r squared. And I know what these are now, so I would have solved for r over here, and I would have plugged that in, and then I know what my g is. You'd expect it to be quite small, and I haven't solved it myself, and I assume that it will be a fraction of the gravitational field strength here on the Earth. Now, do you have to worry about the satellite crashing into the International Space Station? No, the International Space Station is really close. As we saw from problem number 10, it takes about 90 minutes, an hour and a half, as compared to 24. So as I get further and further away, the period becomes greater and greater, and the speed becomes less and less. So not only does it have to go a further distance to complete that circle, but it also will go slower at that further distance, making the period larger and larger. So let's see here. Do I have to worry about International Space Station? No. Do I have to worry about the moon? Well, how long does the moon take to go around? Not 24 hours, but more like 28 days. So that's going to be even further away. So I don't have to worry about crashing into the moon or crashing into the International Space Station. International Space Station would be somewhere in here. The moon would probably be somewhere way out here.